presentation. Actually, I'll just go to the next slide here. The presentation today will consist of kind of the foundation for large assembly considerations. There's some things about your basic computer that you're using that are probably worth knowing, and we'll cover the impact of partial versus full loading, talk about load options. I did some sample large benchmark data just a day or two ago to take a look at disk size versus RAM memory size, and the answers were kind of surprising. And to foreshadow a little bit, if you're not on a 64-bit computer, I think now's the time. These things are getting really large. And then we'll cover display settings, and then get into monolithic versus traditional assemblies, just a quick discussion on those. And it looks like I have display settings listed twice. That's not going to happen. And more topics to come in part 2. And the second part, what we'll do is everyone who emailed and registered on this one, we'll just send out a note when that's produced, and it'll be produced here in the next few days. So we'll just get it out to you. So to start out with, there's a few basic things you can do on your computer or as IT policy that really affect large assembly load times. And one of those happens to be the antivirus. The scanners are taking a lot of time, especially if you use the heuristic real-time protection, which most everybody does. I found a considerable improvement by simply masking off the Unigraphics part document type and the process ugraph.exe for NX. That can improve the stability of NX and load assembly files considerably faster, as they won't be scanned as a matter of normal policy. The other thing, on laptop computers, using the full performance or maximum performance setting has a real impact on the overall CPU temperature and the speed at which NX operates. I've shown some sample settings here that are really good. These may vary with your laptop machine, but in general, an energy saver or a balanced setting can affect the assembly display render speed. The next thing is to talk about NX and the CPU. This is a default, but we have found it out there not set correctly. And NX will use multiple CPUs when it can for rendering and some other tasks. So the two steps are to make sure the environment variable shown there, UGII underscore SMP underscore enable equals 1, set that. And then when you run NX in the log, you will see that it shows the multi-core CPU in the log. And there on the screen, the C processors equals 8. That's what you need to see. It will also tell you, by the way, what NX sees in terms of your CPU, what your caches are, and your total memory, and your swap space. So this 12 gigabytes here that's shown, that's the system memory. If you stay within that, you won't be using your swap disk space. If you exceed that, on this particular machine, I have 24 gigabytes of swap space available. If an assembly gets that big, I'm done. This machine won't be able to render it. So that's a quick way to understand what NX sees in terms of large assemblies. Then another issue is whether or not your GPU is being used. We've seen this a time or two, and I've struggled with it personally a time or two. NX tends to pick up the graphics adapter when it's properly configured, but it may not always do that. And if you're experiencing slow assembly manipulation on, say, 20 or 30 components, there's a real good chance you're not actually using the GPU. So the steps to take are to fire up NX, and then you go look through for, like you can do a search on GL underscore max, and that will get you right near the lines that tell you what graphics device you're using. So I have two sample logs here. You'll see that the NVIDIA one is on the top, and the Intel integrated is on the bottom. The Intel integrated is a very, very common motherboard type graphics, which is good for business, PowerPoint, those kinds of things. But it really won't render a model very well at all. It's about 20 times slower. And the effect of that is on having a part or two on the screen you really don't notice. When it starts to show up is when you get to 10, 50, 100 parts. That curve is kind of exponential in terms of the display demands for the assembly. And we've got some recommendations. Over the last few years, we've seen people kind of struggle with hardware, whether or not to upgrade, how much RAM is appropriate, and we feel pretty comfortable these days saying you need 8 gig of RAM to really run this stuff properly. If you run just booting up a Windows 7 machine, you can end up with 3 gigabytes in use just by having Windows and Microsoft Office. We've all got our Word docs and our emails and a variety of things we're working on. That stuff can consume about 1 gigabyte pretty easily. A 32-bit computer only has a 3 gigabyte memory space, so NX gets very constrained very quickly on a 32-bit computer these days. So it's time for 64-bit. Then the next thing is consider a solid-state disk or high-speed 7200 RPM hard disk on your local machine for best large model performance when loading locally, or if you're in the managed Team Center environment, the Team Center client cache is kept on the local machine. This can greatly speed loading large assemblies as that stuff is cached locally on your hard disk on the computer. If you're transferring data over the network, which a whole lot of people are, Gigabit Ethernet's kind of the minimum recommendation now. All the stuff runs on 100T, but the file sizes and transfer sizes are just getting big enough that it should be running gigabit. Avoid wireless where load times are important. I almost didn't put this one on here because sometimes wireless is actually quite good. But if you're experiencing load times and you're on wireless, that's one of the first places I would look. Latency can be pretty high on those. And if you're on the fringe or there's conflicting wirelesses in the area, you may not get a clear channel, and your transfer rate might actually be really slow. So that's worth taking a look at. Acuity has for a very long time recommended the NVIDIA Quadro series graphics. That's a standing recommendation. There's other vendors out there, but those have, over the years, proven to be the ones that run the most reliably and deliver the best performance. And they are about 10 to 20 times faster than the integrated cards that you'll find, and that's a significant, again, that goes back to that exponential curve. Game cards can be run. We have people out there running them, and they're fast. Sometimes they're very fast. But you may experience, they may not render, and you may have object selection problems. Like the most common one we see is somebody will move over an object to highlight it, and it will stay highlighted. Everything else works fine. So we just want to put a caution out there on the game cards. They're about half the cost of the Quadro cards, but for large assemblies, the price difference is worth it. So now I've got a short presentation here. And this is a presentation that will cover partial versus full loading, and it takes a look at the model RAM size on the computer. I've got the task manager up in the corner, and just going to step through this thing.
This is a quick run-through of opening an assembly, setting load options, comparing memory usage on partial loading versus full loading. So I've got my system here at idle, and it's running right about 2 gigabytes, running screen capture program, operating system, and a few other things. Microsoft Office could add another gigabyte to that, actually. And the system memory total is 12 gigabytes. So I'm going to go ahead and fire up an NX session. NX itself doesn't take a whole lot of memory. Just a few hundred megabytes there. Now this assembly is going to be an airplane, and we need to set the load options for it. NX load options control how NX opens an assembly, and I'll go through the options here, but the main one is that you can save to a file, open to a file, open from a file, and save as default. So I'm going to open from a file. This is the file that I saved with the assembly. People put these things in various places. Some of them put them with the assembly folder. Some of them put them on network drives. Here they're with the assembly folder. And let's go through the options. So first thing is, search folder is the one that's picked. NX will look through all those folders to find the parts for the assembly. You can also choose from folder, which means NX will look in a certain folder. And you can choose as saved, which means NX will go where it saw the part last. Next, we've got structure, and you can do all the components as saved or structure only. Structure only means just get the tree. All components means get everything. And as saved means get the combination of things that were open last time, that were loaded and unloaded last time. Use partial loading means only grab the image of the part, not the full geometry and the history. Use lightweight representations. That one means to get any lightweight geometry that there is. If you've generated those, NX will fetch them automatically and use them. And interpart data is for wavelengths. If you haven't wavelengthed your parts, then you don't need to worry about this. If you have, you can control whether or not that data gets worked in as well. In terms of load behavior, allow replacement means that if you're missing a component, you can pick an alternative one. Generating missing part family members, that's pretty obvious, but it will generate all the missing parts in the part family. And cancel load on failure is just a safety condition. If you want a perfect load, you set that one. Reference sets come down to, if you don't do anything in here, it's as saved. Otherwise, you can choose reference sets that you want to apply to the assembly levels. And finally, load options are complete. And I'm going to go ahead and open the assembly now. So the structure doesn't take a whole lot of time. It's quick, just a couple of seconds. NX grabs all the data it needs, only uses a little bit of memory. And as a quick dry run, I'm going to take this electrical system and partially load that. So just check the box, and NX will go fetch all those parts. And the size of this was 262 megabytes on the disk, and the in-memory size is quite a bit bigger than that. You can see that we're up to, once it gets done displaying, it'll be somewhere close to 3 gigabytes. So the parts have been loaded. NX is generating the display. You can see the bounding boxes there. Finally, the display gets refined, and the assembly is partially loaded. So this is a pretty lean way to do large assemblies. You should partial load whenever you can, because you've got enough to see and work with. And if you want to make anything a work part, NX will just edit it. It will just open it. And you can load individual components if you want to. So now I'm going to close the assembly. And you notice the memory doesn't quite all go away. And I'm going to turn partial loading off. Go right back in. Load it again. Now this time we got the structure, but now it's a full load of this electrical system. So the same size assembly. Now it's going to take considerably longer to load up. I think I may have edited a little chunk of this out, so if you see the progress bar jump real quick, it may have taken a little longer than you see on the screen. So while this is loading, you can see the memory is now well over 3 gigabytes. This is kind of the limit of a 32-bit computer. If you were to have Microsoft Office open right now, you'd be swapping onto your hard disk, and performance would be very slow. So there are the bounding boxes, and the display slowly building up. A quick look at the hierarchy. You can see the load icon there. All these components are fully loaded. If they had part history, which these do not, that would all be in the memory and take up quite a bit, more than the 200 megabytes that's on the disk. So I'm going to close everything up, and you see the memory drop back down, but some remains cached in your system. What's worth noting here is if you close your session all the way, you can recover all the memory. So if you've been working with large assemblies, it's not a bad idea to shut NX all the way down. See, it drops all the way down to the original 2 gigabytes that we started with. And then firing NX back up would kind of as a fresh start. On a very large assembly, that could impact your performance.
So we've got some sample benchmark data for you guys. We have a machine here that had 12 gig of RAM, a 2.5 to 3.2 gigahertz laptop, solid state disk, Windows 7, using NX 8.5.2. The assembly that we just watched, that was a 270 megabyte on-disk assembly. Partial load was 20 to 30 seconds. Took about 900 megabytes of system RAM. A full load took 1 to 2 minutes, 1.5 gigabyte RAM size. And then Microsoft Office, typical documents, opened up, added another gigabyte, and that was 1,000 components, but it was bodies only. So they were either wavelength or JT parts, or there was a few of them that were simplified, or the non-geometry representations. So this is kind of the upper limit of 32-bit Windows 7. If you're doing model history, you've got wavelinking and some other activities going on, you could run into these limits really easy at 100 to 200 components. And if you're adding Team Center on top of the list, then you might only get to 25 or 50 components before you really start to see the system bog down. So we also ran a large benchmark, and same machine, but this time it was the full airplane. It was a large model, 5.2 gigabytes of on-disk data for NX. Full load took 9 minutes, and that peaked out at just a little under 12 gigabytes of RAM. So that was the limit for this machine without Microsoft Office. There was no room to load Office without pushing it into Swap. That had 12,000 component bodies only, and it would be impractical on a 32-bit PC unless you're working with very small portions. Loading MS Office would result on Swap, and again, due to the system RAM on this particular machine. So we thought we'd throw those two data points out there for you to understand, what is large assemblies. There's worth some comments on that. The idea that you can get 1,000 components really varies based on what the components are. If it's architectural steel, maybe you're building towers or something, that's a pretty realistic number. If you're working with plastic parts, you might only get a fifth of those components before you see a lot of assembly issues on your machine. So this next presentation is just a rundown of what the display settings do. We get a fair number of calls. People say, well, I'm on a large assembly. My computer's running slow. I don't understand why I can't spin the model. So we thought we'd just put this out here to clarify what the different settings do and what you can expect.
In this session, we're going to take a look at the graphics options that NX has for dealing with large assembly models. I've got the assembly mostly loaded here, minus the exterior and the electrical system, so we can see some of the part detail. Visualization preferences are session preferences, so when you come into the system, you can tune these for the model that you're working on at the time. These don't really persist from NX Run to NX Run. You use the customer defaults for that. So the first thing we're going to do is set the view animation speed. You notice it's set to smooth. When NX has to transition a view, it will build lots of frames. This looks pretty nice, but if your model is either very large or your graphics system slow, it's very expensive. It'll take a long time to draw. Intermediate cuts out most of those frames and gets right to business. It just transitions to the view with maybe 1 or 2 frames. On the large model tab, automatic is generally pretty good. If you're not having any trouble, this is the setting you want to use. NX balances everything and monitors your graphics performance and just keeps things running as smoothly as it can. And it keeps the detail as high as it can. To illustrate what these functions do, I'm going to go ahead and set it to automatic, and it'll light up the different options in the form. I'm going to do this backwards. I'm going to use the still frames to show you what levels of detail do, because they show up good in the movie capture. So you notice here that all the edges get polygonized and the detail gets low. That's done for speed on very large models, so that's what low detail is. When you go to full detail, it draws every polygon in the model, and regardless of what your zoom level is, it does that work even on large objects or small objects. The next parameter is the filter by screen size. This one's kind of nice because you can set a certain screen coverage. Here I set 20% of the screen. And you'll notice as soon as I hit apply, some little objects disappear. So that little fitting where the cursor is, when we zoom in, you'll notice that NX will start to draw it. That's really handy for models with lots of fasteners, rivets, and small detail. These things can really slow you down, and NX won't draw them until you're zoomed in. And you can see there as the plane zooms out, more and more of it disappears as it reaches the 20% level. Normally, you don't set this for still frames. You want to put that to a small number, maybe get rid of rivets or something. And you want to make these adjustments on the moving frames. The moving frames per second, has a little bit of impact on your rotation speed. Used to be that this would lock the speed of NX rotation. What they've done now is it more or less goes as quick as it can, but it'll try to hold a minimum frame rate. So that's a little bit different behavior than you're used to in the past. And in terms of detail, the low detail setting is really nice for large models. You can rotate around the model quickly, and then the still display will show you the full detail as soon as you stop moving. And on a good graphics system, you can probably set these to the middle and get a good overall balance. Maybe turn up your screen size, and that's a pretty effective combination right there for rotating large models in NX. In the General Graphics tab, these options here, you can turn these off on slow graphics systems like an Intel graphics system. They will do some damage. You can get some speed out of it. The repair incidental display damage really doesn't show up much on either smaller models or fast graphics systems, but the difference really is whether or not NX will watch to see if you're busy before preparing the display. If you're really fast at clicking and you have large models, you might want to pick in idle time there. Finally, there's the Evaluate Graphics Performance, and you turn the checkbox on for Retain Analysis Data. When you run that, NX will keep it from session to session, and it'll tune its performance to your workstation. Lastly, in the Visualization Preferences, you can set the level of faceting detail. On some models, you'll see rough edges, and when you do that, aside from the motion, you can change the level of detail that the system uses to calculate everything. So you'll see there that things get really coarse. You'll see some polygonized edges. You can turn that up to ultra-fine or user-defined and sharpen up the look of things. Maybe you're wanting to do a marketing image or a screen capture. And the ratio slider there controls the level of detail from 1 to 10 if you want to do it manually. Finally, the Update All Objects means that it will draw everything on the screen regardless of whether or not you can see it. It doesn't seem to affect the performance much on the better graphics systems, but on the ones that are slow, that can be a really valuable setting. In this session, we're going to...
So now we're going to move on to monolithic versus traditional assemblies. Monolithic assemblies are, well, actually I have them reversed there. Let's talk about traditional assemblies first. Traditional assemblies are basically part files that contain references to other part files, and they contain components essentially. So if you use the create new component or add component command in NX, you went ahead and made a traditional assembly. And as most of you know, all of you probably should know, the minute you do that, you've got an assembly, and that's just how NX works. There's no special assembly part or workflow that's required to make a traditional assembly. Some attributes about traditional assemblies are that they use components, they have an assembly structure, they can be constrained, and the load options form applies to them. So as you're building up very large models, traditional assembly has the advantage of being able to, you can filter out the different components, you can partially load, you can do alternative representations. So traditional assemblies can grow to be very, very large models. The other thing about traditional assemblies that's kind of a downside is that more management is required for a traditional assembly. You might find yourself setting up load paths, or if you've got lots of files in lots of places on the network, and you need revision control, you may need the data manager to help you with that, because the work organizing traditional assemblies may well exceed the value they bring to your workflow. Monolithic assemblies, on the other hand, are also something I like to call the old school assemblies, because way back in the day, that's pretty much what you did in Unigraphics. We didn't have traditional assemblies until more recently in the software. Monolithic assemblies use solid bodies and sheet bodies in a part file that people just call an assembly. And what happens there is there's no or minimal assembly structure, and I'll explain the word minimal in just a minute. There are no assembly constraints, and the load options may apply, but only if you do a hybrid, a combination of the two techniques. So the reason I threw this in here is there's a lot of cases where you've got assemblies that say they came from vendors, or you want to send an assembly to a vendor, or you're just in a place where you know something won't change, or you need to work on a team, have a team be able to reference geometry without changing or checking out the geometry. A monolithic assembly can be used for all of those tasks, in that what you'll do is you'll put all the solid bodies that represent components into a part file. And if that part file gets output as a step or an IGES, it's all one unit, and that can help you in terms of the number of files and the detail of your assembly structure. So for some types of bill of materials, for example, it isn't really necessary to go all the way down to the lowest levels of detail. If that matches your bill of materials, monolithic assemblies can save you time on certain classes of parts that don't change or that are standard. And some examples of that might be motors, actuator cylinders, things that you'd buy that are small subsystem type assemblies would be a good target for the monolithic assembly.
In this short video demonstration, we're going to take a look at the difference between a monolithic assembly and a traditional assembly and make a couple suggestions as to how they might be used. To start out with, we'll open up a traditional assembly. This is the right-hand landing gear from the airplane seen in earlier videos. You can clearly see here it's a traditional assembly. It's got a hierarchy, levels of components, all the usual things we'd expect. I'm going to run the open assembly command on it, pull in all the parts. And there it is. You can see that there's a number of components in this thing. And the yellow part in particular is actually a vendor part. That's actually a whole sub-assembly that's just brought in as a lightweight body. You can't really do anything with that. It's just there to look at. You can see here there's a component highlighted that's also a monolithic assembly in terms of there's many different parts in a given component file, and that's really the key to understanding these things, is there are solids actually in the assembly files. Now notice there's no solids in the part navigator here, so this assembly file is actually pure. It has components. Some of those components may be monolithic, but it is actually a traditional assembly because it has no solids in the assembly file itself. So we'll close that one up. And now we'll open up a monolithic one. It's the same exact assembly, only just done differently. So here's all the parts. We'll wait for these to render. Now you can see that the hierarchy's gone. There's still that vendor part. So that lightweight body's still there. Still take a look at it. It's still a component. But the big difference is the other components aren't listed in the assembly hierarchy anymore. Those are now solids or sheets contained in the main assembly file. This can be used to simplify things or build representations and export them to people without them changing or exposing the constraints or even all the IP. You can simply leave some of the parts out. Now, if you look in the part navigator, all the components are now represented as sheet bodies. You can see them there one after the other. Those could be renamed too for convenience. Some of them are sheets, some of them are solids. Let's go ahead and highlight a couple of sheet bodies. That big thing is still a sheet. Brake assembly is a sheet. And the tire and a few other things are solids. So in the case that we have here, at the monolithic assembly, you're really talking about packing a lot of data into one part file. If this were exported to somebody, they would get everything except for the yellow piece, and that would just be a component that doesn't have a file. The rest of the assembly is rigid and accessible to them for measurements, building fixtures, and whatever else they'd like to do with it. The other thing you can do with this is wavelength. You could wavelength the parts and bring bodies into an assembly file for reference if you like. In this short video demonstration.
So that concludes this part one of the large assembly lunch and learn. The next one will contain some detail on constraints versus non-constraints and using coordinate systems in a large assembly context. Again, as mentioned in the first part of the broadcast, this is broken into two parts. So anyone who emailed or registered for this one will get a notice on the next one, and we'll produce that sooner rather than later and get the video out to you guys. Thank you very much for your time, and thank you very much.